Hi, today we'll be continuing with Section 3.3, the addition rule. If you'd like to, I included some videos that kind of explain this topic a bit more. All right, let's begin with our notes. So to begin, let's start with the definition of mutually exclusive and non-exclusive. Two events A and B are mutually exclusive when A and B cannot occur at the same time. That is, A and B have no outcomes in common. So when we think of A and B, think of these as two different events, event 1 and event 2. But in math, we like to refer them as two different cases, A and B. That's where those letters come from. So here are two Venn diagrams that illustrate what happens to mutually exclusive and not mutually exclusive. So mutually exclusive, here we have two pictures. We have this picture here, and we see we have two different cases, two different events, event A and event B. And we see that there is no overlap. Each event is separate from the other. Mutually exclusive means they have absolutely nothing in common. In the next box, we have not mutually exclusive. And here we see that we have two pictures and they have some common ground. There's something in common, right? Mutually exclusive means that they have some value in common. So when we are considering a type of probability, we have to take in consideration, we will see this in the formula. So example 1, there are two events to consider. The first event is called event A, and the second event is event B. Determine whether the events are mutually exclusive. Explain your reasoning. All right, so here are our examples. We have event A and event B with three different problems. Let's take a look at the first one. 1. Event A, roll a 3 on a die, and then event B, roll 4 on a die. Okay, so each time I roll a die, I can get one of 6 numbers. But if I get a 3, and then I roll again to get a 4, does each time I roll, does the number I have before it affect my roll each time? Do they have anything in common? No, right? Each roll is separate. So here they are mutually exclusive. Each roll is different, it's separate. So each roll is not affected by the previous. All right, next example. Event A, randomly select a male student, and event B, randomly select a nursing major. Okay, my first event is choosing a male student. My second is to select a nursing major. Can there be some overlap? Yeah, right? So here they're not mutually exclusive. Not mutually exclusive. And this is because there can be a nursing major that is male, right? Because there can be a nursing major that's male. They have something in common. All right, problem 3. Event A, randomly select a blood donor with type O blood. Event B, randomly select a female blood donor. Okay, is there anything in common? Yeah, there is a possibility that these two events can overlap. There can be a female that's also a blood donor with type O blood, right? So this one is not mutually exclusive because there can be a female blood donor with type O blood. All right. So when we work with these problems, we have to be careful if they're mutually exclusive or not. And these are some examples of what we mean by mutually exclusive. All right, we're going to continue with the addition rule. It reads, this is where our practice from example 1 comes in handy. There will be problems where we have to be careful of situation where they have something in common, meaning the events are not mutually exclusive. So this is chart and formula from page 158 in your text, and we have two formulas to consider. The first one is when they're not mutually exclusive, meaning they have something in common. If not, then I have to take my event A and my event B, take each probability, and then subtract what they have in common. So that part where they overlap, we need to subtract that. Because if I don't, then essentially we're upping our probability because there'll be some type of double dipping. 2. Mutually exclusive, meaning they have nothing in common. If so, then I take my probability for one case and my probability for the second case or event, and I add them up. All right, let's take a look at this example. And I like this one because it has a picture so we can see what it's referring to. So, example 2, problem 1. You select a card from a 52 deck of playing cards. Find the probability that the card is a 4 or an ace. Okay, so let's take a look at our two events. Our first event is that it's a 4. Our second event is that we get an ace. Here we see that they're looking at the picture, there is nothing in common between these two. Having a 4 has nothing to do with getting an ace. So let's consider each event. So for this one, we see that they are mutually exclusive. They have nothing in common. So therefore, out of our two formulas above, which one will we use? We'll use the formula 2. Okay, so what's our probability of A? Getting a 4. I can get a 4, and that's 4 out of 52 cards. And then my next event is B, getting an ace. The way I can get an ace is 4 out of 52. So therefore, our answer, we have a common denominator, is 8 over 52. And from there, we can just punch it into our calculator and round to maybe 2 decimal places. I'll let you do that. Let's go on to the next one. Number 2, you roll a die. Find the probability of rolling a number less than 3 or rolling an odd number. So here are two events. Our first event, event A, is less than 3. Our second event, event B, is rolling an odd number. All right, so let's think of what numbers are less than 3. 1 and 2 are less than 3. What are odd numbers in a die? Remember, we have a die. A die is includes numbers 1 through 6. So our odd numbers be 1, 3, and 5. Here we can see a picture, and we see that of odd numbers, we have the numbers 1, 3, and 5, and less than 3 are numbers 1 and 2, and we see that they have this 1 in common, right? So here in this problem, we see that they're not mutually exclusive. Okay, when it's not mutually exclusive, which formula should we use? Well, we see above, when they're not mutually exclusive, we want formula 1. So meaning we have to take the probability of A, add the probability of B, and then subtract the probability that they have in common. Okay, so let's consider our cases. For probability of A is rolling a number less than 3. So that's 2 out of 6, 1 and 2, two different things out of 6 possible. B, getting an odd number, 1, 3, 5, so that's 3 out of the 6. And then I have to subtract what they have in common, just one number out of the 6 possible numbers. 2 plus 3 is 5, minus 1, we get 4 out of 6. And we can punch that into our calculator, round to decimal places, and they'll give us our probability. So when you're punching this into your calculator, you're punching it as 4 divided by 6. Top number divided by bottom number. All right, let's continue with our last question. Example 4. A blood bank catalogs the types of blood, including whether it's Rh positive or Rh negative, given by donors during the last 5 days. The number of donors who gave each blood type is shown in the table. So let's take a moment to analyze our table. So we have our blood types O, A, B, AB, and then the total of each one according to its Rh factor. We usually just refer to it as positive or negative, right? So here I see that I can have positive O, positive A, positive B, positive AB, and of all the positive blood types, we get a total. We also get a total vertically of each blood type, including both positive and negative, right? And we get a number for each one. And we also get a special total of all the numbers. Okay, now that we took a moment to analyze our graph, our chart, let's go ahead and answer the following questions. 1. Find the probability that the donor selected at random has type O or type A blood. Okay, so type O blood is these right here, and type A blood is those right here. Do they have anything in common? No. They would have something in common if maybe we were asked about positive or negative, but they're two different blood types. And each blood type has a total for each one. Okay, so for 1, we see that they're mutually exclusive. And if you want to follow your formula closely, this would follow formula 2. So our formula would be P of A plus P of B, each event separately. P of A, the probability of having O blood, is 184 out of the 409. The probability of B, type A blood, is, O and A. A is 164 and 409. I thought I said B. I think I said B by accident. All right, we go ahead and add them. So 184 plus 164 is 348. Because I have a common denominator, I can just add my numerators. All right, you punch into your calculator. Your answer should be something about 0.851. All right, let's go ahead and do problem 2. Find the probability that a donor selected at random has type O blood and is negative. So let me erase my previous notes. So I want to consider that my donor is type B blood, and I want to consider that it's negative. So we see there is some common ground, right? Even if I didn't highlight it, we could think, oh, well, it could be type B and negative. Let's consider. So this has something in common, so it's not mutually exclusive. they have something in common. And if we take a look back at our previous page, we would want to follow Formula 1. And the reason I like to follow the formulas is specifically for this case where they're not mutually exclusive. We have to be very careful of subtracting that part they have in common. And it can be kind of tricky to set up. So let's write down our formula. Our formula is P of A, probability of event A, plus P of B, probability of event B, minus probability of event A and B, the part they overlap, what they have in common. Okay, probability of A is type B blood. Probability of B is negative. So how many type B bloods do we have? Type B bloods, we have 45 out of 405. 45 out of 405. How many negatives? Negatives, we have 65 out of 409. 409. I'm going to write 5. And then it's minus the probability of what they have in common. So in common, they have just that 8. 8 out of the 409. All right, so we have a common denominator of 409. 45 plus 65 minus 8. We can use our calculator, that's 102. And lastly, you punch this into our calculator, 102 divided by 409, we get 0.04. 0.249. All right, so this is section 3.3. I want to highlight 2 pieces. We learned about mutually exclusive and not mutually exclusive cases, and we have to be careful, look at each story separately, and think if they have any common ground. If so, I want to use one of these 2 formulas. And that depends whether we decide that they're mutually exclusive or not mutually exclusive. All right, that's it for 3.3. If you have any questions, you can post them in our general discussion board or you can email me. Thank you.